In this video, we're going to discuss the plots that would be observed when you follow a titration. So grab a few images from our textbook here. I think they're a little nicer than my drawings. So let's talk about what happens. We're doing a titration here of adding a strong base to a strong acid. When we watch the pH versus our volume, well, we start with a strong acid, so we're pretty low in pH. We add a little base, it consumes some of the acid, but not a lot. So our pH goes up a little. And again, we add some strong base, it consumes some of our strong acid. And then suddenly, very rapidly, we just shoot up to really basic. What's going on? Why does this happen, and what is this plot telling us? Well, let's think about our concentrations for a minute. Let's say we start with 1 molar strong acid. And we'll say it's in 1 liter, so our moles are equal to our molarity. And to this, let's add 0.1 mole of strong base. Well, the consequence of this is what's going to happen to our strong acid concentration. It's going to go down to 0.9. If I've got something like HCl plus NaOH, they're just going to wipe each other out. You're going to get sodium chloride and water. Well, I can add another 0.1 mole, and I'll take my strong acid down to 0.8. The difference in pH between a 1 molar H plus and a 0.8 molar H plus is not that great. Remember, it's an order of magnitude concentration difference for every pH unit, so we're still in the same pH unit. And you can do this for a while. 0.1 mole down to 0.7, add another 0.1 mole of your base, 0.6, 0.5, 4, 3, 2, 1. Even when you've reduced your strong acid down to 1/10 the original amount, that's only changed your pH unit by 1. So for a long time, we see almost no change in the pH. And then, well, we go and we add 0.1 again. And now this drops to 0. Or let's take a slightly finer look. Let's say we add 0.09 this case. It wasn't quite as big a drop. There wasn't quite as much of our strong base. Well, that's going to take this down to 0.01. It took 9 additions to change our concentration down to 1/10 originally, and now it took slightly less than one of those additions to change us by 1/10 again. Suddenly we get in the next addition the same increase as the last 9 additions gave us. So early on we saw almost no change, and then with the next one we see about as much change in a single addition. And then we see way more change for the next addition. What's happening is, if we actually added the 0.1, we would have been 0.0. We would have been no acid. Well, it would have perfectly wiped out the base, and so we had no base. We would have been at pH equals 7. If you'd added exactly enough base to wipe out your acid, you'd be right at neutral. Any extra, even the slightest bit of extra base, would have meant you had significant amounts of base. Now you'd have leftover base in solution. So we would just have that for our concentration. Since there's no more acid, since we'd fully wiped out the acid, the slightest bit of extra base is now the dominant thing in solution at that point. And 0.01 molar hydroxide, there's going to be a pOH of 2, so pH of 12. And that's basically what we see right here. The changes are rapid because, well, it's a log system. What we got for the first 10 steps, we get again in the next one, and we get 10 times that in the next one. When we look at these plots of pH versus titrant added, we have to realize that the different sections are telling us about different things in solution. Prior to completely wiping out, this was acid dominated. There was leftover strong acid. That was what was going to determine the pH. How much strong acid was there? The moment we added just a little extra base, it was base dominated. The amount of extra base that we added was what set the pH. And for an instant, right in the middle, where they just happened to be perfectly equal to each other, well, neither was in solution. And so water, the natural pH of water, was the only source of H+. The point where that occurs is the equivalence point. That was the point where we had added exactly as much base as was needed to consume all the acid. They were equal. Equivalence points come up in other mixtures, weak acids and bases with strong acids and bases. But in this case, when it is a strong acid and strong base, when they are equal to each other, the only thing left is water. And so the equivalence point's pH is 7. That's not going to be true for our other mixtures, though. Let's take a look at one of those. Here's a weak acid and a strong base. So let's talk about the regions here. At the very beginning, we just have our weak acid. So this is purely weak acid based. For this, we'd have to do the calculation of a weak acid separating into H+ and weak base, but you could find that initial pH. For a little while, adding even the slightest bit of strong base can change our pH pretty quickly, because we're not buffering yet. Your buffering range tends to be ±1 of the pKa. As a result, until you get your weak base concentration up to 1/10 of your acid concentration, you're not really in a buffering region. But eventually you get there and, well, it starts to buffer. You're adding base, but it's inhibiting. It's not changing as much as it did early on. You'll notice the curve, if we kind of project the line, was aggressive earlier, but the curve, once you're in the buffering region, is not as extreme. The closer your concentration of your weak acid and base get, the shallower that angle becomes. They are inhibiting the change better. The closer in concentration your weak acid and base are to each other, the better they inhibit the changes in pH. Think about why for a second. Your pKa plus the log of your base over your acid. Well, say we had like 1 molar acid to start with. As you add, say, 0.1 mole of strong base. Well, what that's going to give you is an acid concentration that goes down. 0.9, 0.8, 0.7, 0.6. That's going to give you a weak base concentration that goes up. 0.1, 0.2, 0.3, 0.4. As you take the log of those ratios, however, your log of 0.1 over 0.9 versus log of 0.2 over 0.8 versus your log 0.3 over 0.7 versus your log of 0.4 over 0.6. We can see that the changes introduced get smaller and smaller the closer our concentrations get to each other. So that if we were to shift from a 0.3 base to a 0.4 base and reduce our acid from 0.7 to 0.6, we're only going to see a small change in the pH there, where if we had done that early on from 0.1 to 0.2 and 0.9 to 0.8, we'd see a bigger change in our pH effect. The closer your concentrations are to each other, the less your pH is going to change when an outside source alters them. And so we have a buffer region controlled by the equilibrium expression. Eventually we get to the end of the buffer region, and now adding more strong base ends up finishing consuming all the weak acid. And so rapidly, for a small addition of extra strong base, we shoot up in our pH. In the final region here, this is just strong base dominated. We've wiped out all the strong acid. even though there's some weak base left, it's in equilibrium to make a small amount of hydroxide, but the strong base, we've just added lots. As you continue to add strong base, you just have tons of hydroxide from the strong base. It overwhelms what amount would be created by the weak base and its Kb. And so we have a couple ranges that we find. There's the initial range, which is weak acid based. There's the buffer range, which is equilibrium based. The final bit is just strong base controlled. And in the middle right here, we run into our equivalence point. This equivalence point, however, this equivalent point is when our strong base equaled our weak acid. That's when the base we are adding was equal to the amount of acid we started with, the amount of weak acid that was present. Which means all that's left is weak base. So if we take this to the extreme here, get down to 0.1 and 0.9, and finally 0.0 and 1. The moment I have just wiped out all my weak acid, but have not added any extra strong base. So the only molecules still floating around in solution are the weak base. Well, our weak base is going to attack some water, create some hydroxide, and so it's going to have its pH based on pure weak base, which is why our pH here is 8.79. It's slightly basic. If you've got a weak base in solution and nothing else, then you should have a slightly basic solution. The pH at your equivalence point is based on what species are still in solution. When it was our strong acid and strong base, only water was still in solution. I guess sodium chloride, but that's not a acidic or basic salt, and so it wouldn't affect the pH. The only source of H+ that was in our strong acid base mixture when they were at equivalence was water, and so its pH was 7. But the only source of H+, or in this case OH-, at the equivalence point for this weak acid strong base mixture was the weak base. Right at the equivalence, the only thing left is weak base. And so the hydroxide was set by the weak base. Leads us then to the final one. What happens if we have a weak base and we add a strong acid? Well, just the reverse. At the very beginning, your pH is set by the weak base. How much hydroxide would that weak base produce? Very quickly, as we add some HCl, you end up in a buffer region. And that buffer region is ran by the equilibrium. As our strong acid attacks our weak base, it makes weak acid. And so we can just use our Ka expression and the concentrations of weak acid and weak base. How much weak base is still left? How much weak acid got created when the strong acid removed some of the weak base? At the far end, we are strong acid dominated. Your pH is just dependent on however much strong acid you've overshot by, how much extra strong acid was there. But right here, right at the equivalence point, this is where our strong acid is equal to our weak base. Well, if our strong acid has just wiped out all the weak base, I've added just enough strong acid to be equal to the amount of weak base, then all that remains is weak acid. And so our pH at the equivalence point is just the dissociation of pure weak acid. What is the concentration of weak acid? Set up the Ka expression to solve for how much it would dissociate into. And so these titration curves alter depending on what it is we are titrating with each other. Do we have a strong acid or base that we're adding a strong acid or base to? Do we have a weak acid or base that we're adding a strong acid or base to? These will determine what your starting pH is set by, what your equivalence pH is set by, and why your ending pH will either be very basic or very acidic, depending on if you added strong base or strong acid to the point of excess.